All right, we'll have more time for questions at the end, so I'm going to move into stem cells, lasers, and novel approaches for longevity and cancer. We're trying to lengthen the patient's life in cancer, right? Well, so many of the things that are applicable to cancer patients will lengthen a person's life that may not have cancer. So let's talk about stem cells, because they're really cool, and there's a lot of great new developments in the stem cell arena. So stem cells have the ability to divide and create an identical copy of themselves. It's self-renewing. They can also divide to form cells that mature into cells that make up other tissues, so they can de-differentiate. So a stem cell can become a heart cell, a muscle cell, a bone cell, a brain cell, and that's really cool stuff. So stem cells can potentially aid in the healing of all of these different diseases. So we may be able to renew the thyroid with stem cells, or the thymus, which if we cracked open my chest right now and tried to find my thymus, you wouldn't be able to find it. Well, hello, that's half of your immune system. The T cells, anybody ever heard of a T cell? T is for thymus. So those immune cells come from your thymus. And if you crack me open right now, you wouldn't be able to find my thymus. So thymus renewal, so that your immune system is functioning better. So there's a lot of areas of application. It's not just for, let's go back a second. It's not just for sports injuries anymore. We can do a lot of things with stem cells. In theory, if you gave a large enough dose of stem cells, you could repair almost any damaged organ or tissue that is degenerated. So the capacity to reset the biological age of cells and tissues, including that of DNA and the aging clocks, could be virtually unlimited. So there's a lot of potential applications now under study: reversing hopeless degenerative conditions, repairing otherwise irreversible trauma or spinal injuries. You can cause rapidly dividing cells to revert to normal. That's probably called cancer. And improve the condition of any aging tissue. So there's a lot of things that we can do with stem cells. We can facilitate the healing of acute and chronic injuries. I've had both of my shoulders, which I could hardly wash my hair anymore or reach behind my back, injected with stem cells, and full range of motion now, back to my full exercise routine. I even tried surfing the other day, which requires a lot of shoulder motion. I wasn't very successful at that. Takes a lot of skill. So different types of stem cells. Autologous means your own stem cells. Allo is somebody else's stem cells. And so they're different things. Autologous stem cells, it's our own stem cells. You can get them from your own bone marrow, your own tummy fat, mesenchymal stem cells. There's a new type cell out there that is virtually unknown at present. It's called a VSEL, or very small embryonic-like cell. Now, bone marrow and mesenchymal cells, I've had my mesenchymal cells harvested from my tummy fat. They use liposuction and then they harvest them. I've got them banked down in Fort Lauderdale. But you know what? They're just as old as I am. The telomeres, the thing that allows them to reproduce, gets shorter as we age. And so those cells may have accumulated metabolic damage, radiation damage. They can't divide but a few more times. They're as old as I am. VSELs are really cool because they're embryonic-like. They have a full telomere. They're as young as you are when you were born. They aren't like the other stem cells that we've been hearing about for so long. Allogenic stem cells from fetuses, umbilical stem cells, or you can get them from a bone marrow of another person or fat from another person. They're frequently used for transplants for cancer patients. You've all heard of that process. And they're usually from healthy donors that are cancer-free. One of the advantages is you don't have to have a procedure done on yourself. There's some potential downsides, infection, your body can reject them, and the lack of enough of the cells to persist effective ongoing change. So there's some of the problems. Some of the challenges of stem cells is getting them to go where we want them to go and stay there. Now, if I'm putting stem cells in a joint, yeah, they're pretty much going to stay there because there's not a huge amount of blood flow. But if you had gangrene of the leg and I put stem cells in your femoral artery and they all went into that leg, a couple of hours later, probably 80–85% of them would be gone. 24 hours later, 95% of them would be gone. So stem cells are kind of like herding cats. They go where they want to go. And so one of the problems has been getting them to stay where we want them to stay. If you put them in a joint, no problem. If you're trying to get them someplace else, stay in the heart, go to the brain, the liver, the kidneys, you have trouble. You can even take a catheter and catheterize a coronary artery to get stem cells to a dead part of the heart. Inject them right there. Next day, they're almost non-existent. So if we could find the magic to get them to stay there, wouldn't that be cool? So why current stem cell treatments? You know, we've all heard about stem cells. We've been hearing for them for 20 or 30 years now, but the magic hasn't happened. It's going like, okay. So they're from other people, so that presents a problem. Many times they're not fully potent. They can't become any tissue. They're old. They have short telomeres unless you're using umbilical stem cells. And then getting them to stay where you want them to stay. And then there's VSELs. Really cool. They've just literally been, we've known about them for a few years. There was argument 4 or 5 years back whether they even really existed. They exist. They're actually circulating around in your blood right now as you sit here. So you don't have to do liposuction to get them or knock a hole in the bone marrow and then go through this chemical process to harvest them out. You simply draw blood, like when you go to the lab drawing station, draw blood out of the arm, spin it down, and harvest the stem cells because they're right there in the blood circulating around. They don't do much normally, and we don't know why they aren't active. I call it the Methuselah factor. I think at one time the Earth was probably circled with crystal rings, kind of like Saturn is, that protected us from a lot of radiation and things and created a more standard and constant atmospheric pressure, but that's just my crazy thoughts about it. And it probably protected us from a lot of things that we don't have now after the flood. And so, but one way or the other, these are very small stem cells are mostly just sitting around like not doing anything. So one of the problems has been finding out how to switch them on, how to activate them. We figured that out now. Another really cool thing about them is they're small, very small, they're tiny, and they're truly fully potent. They're as young as you are when you were born, so they've got full telomeres. Now, we've figured out how to activate these with laser optics. And so before, they've been quiescent. We've now figured out how to activate these with certain frequencies of light and light systems, optical systems. So we can quickly and intensely attract the cells with this beam of light to a specific location. And we increase their cellular adhesion properties. Remember, you can't get them to stay where you want them to stay. Well, there's a thing called cellular adhesion where the cells get sticky, and when you get them to a place, they stick there. So the light can increase their cellular adhesion properties that helps them to get them to stay where you want them to stay instead of passing on through. And it also creates communication between the cells. So they start talking to each other and say, oh, you're a heart cell? Oh, I want to be a heart cell too. Can I be a heart cell? Can I join you over here and make you stronger and help repair? Okay, so the cells start talking to each other. There's a lot A lot of crosstalk going on between all of our cells. So we figured this out, actually Dr. Todd figured this out by putting very small stem cells in a blood culture. And then he shined a laser light through it, and what he observed was all of the cells lined up along the light beam. Voila, we found out a way to make them go where we want them to go and stay where we want them to stay. So we can accelerate change in health. We can accelerate healing with the laser-guided stem cells. So they're activated by the light frequency, and it results in clinical improvement many times within 24 hours. Average for stem cells is weeks to months. And ultimately, you get symptomatic and objective recover many times much quicker, as was illustrated in a heart study that we did in Europe. So the optical laser guidance process, it's patented, it's proprietary. The cells are first pre-activated with the optical laser system. That brings out those cellular adhesion properties, and that helps them to start dividing. Because when they get where we want them to go, we want them to start growing. Because you've got a part of the heart that's dead, or part of the spinal cord that's damaged, or part of the brain that's not working anymore, the substantia nigra, and you get Parkinson's. So there's parts that are broken that we want to fix. We want new cells to come there. We aren't going to fix them. Your body's going to fix them. Your stem cells are going to go there, become that kind of cell, and start growing. So we want them to start growing, and that does that. So after we harvest them, activate them with the optical laser system, and then we put them back into the body, right back in the vein where we got them out, and then we guide them where we want them to go. So you have a Parkinson's patient. Now we don't treat anything with these. Your body is going to do it. We guide them to the broken area, to the area that they want, and then the body, if it chooses to do so, is going to do the healing. So I'm not a healer. In this case, I'm more of a technician. We're gathering your stem cells, activating them, and then trying to guide them to a certain area. And then your body is going to make the repairs that it wants to repair. So evidence of efficacy, we did a congestive heart failure. A lot of these people were on heart transplant list, and what we got was an 8% increase in function. That's the average. And what we got was a dramatic increase in statistically significant function. So normal cardiac output is around 50 to 60%. Ejection fracture, heart failure is less than 50, moderate, and then severe is 30. So this study was actually published in the European Heart Journal, where we got a dramatic increase in function in a very brief period of time. So laser guidance, the laser activated guided stem cells gave a 3% increase in ejection fracture in 3 days. Remember, it usually took 180 days to get an 8% increase. We got a 3% increase in 3 days. With low starting ejection fractions, that was a 14% improvement in 3 days. So quite significant results. So that our results were 60 times faster when we used laser activated and guided stem cells than cardiac catheter guided stem cells. And how did we do this? We harvested stem cells, laser activated them, put them back into, and then we aimed the optic laser system through the heart, changing the direction because we wanted the laser system to be constantly going through the heart. We didn't just stay one direction, because then you're getting the lungs, the ribs, the spine, all that in between. So we kept changing the direction but we were keeping the heart in the center of our beam, because that's where we wanted the cells to go. And so that's how we did that. So all end-stage case candidates for heart transplant, or they were on a recommendation for a ventricular assist device. The improvement statistically was significant, was greater than the P of 0.01 for all measures from days 3 to 9. 50% average increase in heart function, 50%. 50% of patients improved off the heart transplant list. 20% improved to nearly normal with one treatment. That's phenomenal. So that was a heart study that we did in Europe. Additional clinical evidence, we've had significant improvement within 24 hours of stroke, Parkinson's, multiple sclerosis, amyotrophic, cerebral palsy, spinal injuries. So this is beneficial, especially for neurological conditions, it would appear. But theoretically, you can regenerate most any organ or tissue with the stem cells, because remember, they're omnipotent. They can become anything. Just a matter of guiding them to the area where you want them to do the repair. Now, do we treat ALS or stroke or Parkinson's with this? No. A patient may come to us with that. It's not indicated for that. If they come to us, we will guide stem cells there and let them do their magic.